So the additive counting principle says that if one mutually exclusive event can occur in m ways, another in n ways, and another in p ways, and so on, then the total number of ways that these events can occur is m plus n plus p, etc., etc. We'll take a look at this additive counting principle in this next example. In a standard deck of cards, there's 52 cards and there are 4 suits. How many ways are there to select a card that is either a red face or a black ace? Well, first of all, let's set into motion what are our red face cards. There they are there. The king, the queen, and the jack of hearts. The king, the queen, and the jack of diamonds. So there are 6 of them. And of course our black aces, there are 2 of them. The ace of clubs and the ace of spades. And so how many ways could we select a card that is either a red face or a black ace? So if you reached in, how many different possibilities are there? The key word here is or. This word or, you're going to see it over and over, and or means to add. A card that is either a red face or a black ace. Are these events mutually exclusive? Can you reach into the deck and select a card that is both a red face and a black ace at the same time? And of course the answer is no, you can't. So these events are mutually exclusive, which means that we can use the very straightforward method of the additive counting principle to say, hey, the number of ways that we can select a red face or a black ace is 6 plus 2. So there's 8 ways that we can do it. But what if you wanted to find the ways to select a red face and a black ace, one after the other? And of course the key word here is the word and that means to multiply. And so then we can say, okay, well the number of ways that we can select a red face and a black ace is 6 times 2, which is 12. So there are 12 ways to select both of those, one after the other. Now, let's take a look at this next question, a heart or a queen. How many ways can we select a heart or a queen? And of course the question is, first of all, are these events mutually exclusive? Could you select a heart that is a queen and have it be the same card? And the answer is yes, you could. So these events are not mutually exclusive. So we can't simply use the additive counting principle and add up the number of hearts with the number of queens, because there's a little bit of an overlap here. What we need to do is that we need to separate them out and count them very, very carefully. So here in the first part we have hearts that are not queens. And there are 12 of those because there are 13 hearts. So if we get rid of the one that's not a queen, we have 12. And to that, we will add the one case where we have a heart and a queen, the queen of hearts. There's only one of those cards in the deck. And the last piece that we're missing here is the number of queens that are not hearts. So the queen of spades, the queen of clubs, and the queen of diamonds, and there are 3 of those. And so we've been very careful to count hearts and queens so that we don't get any overlap and we don't double count. And of course the answer when you add these up is you end up with 16. Now had we simply added the number of hearts in the deck, which is 13, to the number of queens in the deck, which is 4, we would have had 17, and that would have been too many. That's the incorrect answer. So when events are not mutually exclusive, you need to be a little bit more careful to add things up so that you're not double counting. Using the digits 1, 2, 3, and 4, allowing for repetition. So we're going to repeat these digits. We don't have to worry about that. How many 2-digit numbers are possible? Well, here's our things that we're going to select. A 1, a 2, a 3, or a 4. And how many 2-digit numbers are possible? So we only want 2 digits at a time. So how many options do we have for the first digit? Well, we have 4 because there's 4 things to choose from. And so for the first digit, we'd have 4. We're allowed to repeat. And so how many choices would we have for the second digit? Of course, the answer there is 4. So because a 2-digit number is the first digit and the second digit, you can't have a 2-digit number that's not both, we multiply them together and we get 16 possibilities for the first, for 2-digit numbers. How many different 3-digit numbers are possible? Well, again, we have 4 choices for the first digit, 4 choices for the second, and we have 4 choices for the third, so the number of 3-digit possibilities are 4 times 4 times 4, which is equal to 64. And that's because a 3-digit number is the first digit and the second digit and the third digit. So now, how many different 2-digit or 3-digit numbers are possible? Well, let's ask ourselves this question. Can a number be 2 digits and 3 digits at the same time? And the answer is no, it can't be. A number is either, it either has 2 digits or it has 3 digits. It doesn't have some wacky combination of both. So these are mutually exclusive events, so we can simply add the results from A and B, and we get 80 2 or 3-digit numbers. Let's take that approach of numbers and make things a little bit more broad, using all of the digits from 0 to 9. How many 3-digit numbers are possible, allowing for repetition of digits? So 3-digit numbers, but now we have everything from 0 to 9. So the number of 3 digits allowing for repetition. Here's our 3 spots. This is going to constitute our digit. And so in the first spot for the first digit, how many options do we have? We have anywhere from 0 to 9. So that's what we can use. But in the first spot, how many options do we have? Well, if you're saying 9, you are on the right track. And of course, why do we only have 9 possibilities for that first digit? 0 to 9 is 10 distinct items. But why are there only 9 distinct items for the first? Well, the answer has a lot to do with, hey, if it's a 3-digit number, then you can't use a 0 in that first place. Because if you do, then you're down to a 2-digit number. So if it's a 3-digit number, we can't use a 0 in the first spot, and so we only have 9 choices. If we're allowing for repetition, how many choices then would we have for the second number? Because now we can use 0. So now we have a full 10 choices. And likewise for the third. So we have a total of 900 numbers that have 3 digits using the numbers 0 to 9, using the digits 0 to 9. So let's look at another restriction here. How many 3-digit numbers are possible where there's no repetition of digits allowed? So 555 would not be an allowed digit here, would not be an allowed number. So the number of 3 digits without repetition, well, let's set up our 3 spots. How many choices do we have for that first digit? We'd have 9. And for the exact same reason as above, if it's a 3-digit number, we can't use a 0 first. How many choices now, though, do we have for the second digit? We can use 0, but we can't use the one that we've just used in the first. So we're back to 9. And of course, we can draw this and we can say, hey, we can use a 0 in that spot, but we can't use the number that we used in the first place because we're not allowed to repeat. So we've got 9 options. And in the last spot, hey, well, now we can't use the number that we used first and we can't use the number that we've used second, so we have 8. And the total here is 648 3-digit numbers where we don't have repetition. Question number C, we're going to leave for you to solve on your own. How many 3-digit numbers are possible that contain at least one 5? So at least one 5 means 1 5 or 2 5s or 3 5s. And that gives you a hint that repetition is okay. So try this one for yourself and see if you can get the answer of 252.